All right, guys. So the universe doesn't seem to want this video to be made. But I'm gonna fight through it. This is the second time I made it because the first time the microphone turned off mysteriously. So, and then I tried to make it again, and when I hit record, my computer shut down. All right. So anyway, take three. Let's go. I want to talk about the three Beaker question. Okay, we have variations of it. We're going to do one in class, or we did one in class. We're going to do another example of one today. I'm just going to walk you through it. If you really understand it, you're in really good shape when it comes to what we're discussing in Unit 5. So if you don't understand it, figure it out. Watch previous videos. Look at the PowerPoint. Come get extra help. All right, but you got to figure it out, right? So the reason I like this question, this is an actual old AP chemistry question. So all the variations that I have for you are inspired by a question that was on the AP exam a few years ago. And it's a really good question. So again, first you're kind of looking at three different solutions in the three different beakers that haven't been mixed yet. And you want to be able to answer questions about each solution on their own. And then you start mixing the solutions together, and you got to know what's going on there. Okay. So let's look at the question. So the one I want to go over today starts out like this. And if you don't want to watch the video, at the end of this, there's a kind of written explanation on all the answers. But the first thing I'd like you to do is, before you even read any of the questions, before we even jump in and read the scenario, we just want to talk about each individual solution as their own thing. So we have a solution of potassium hydroxide. We have a solution of potassium acetate. We have a solution of acetic acid. So we kind of want to, like, what do we know? What can we understand? What can we calculate? Just looking at each solution and knowing what each solution what's really going on in each solution. Okay. Another thing to look for right off the bat are the amounts. So notice all the solutions have the same molarity. So the molarity of acetic acid is the same as the molarity of potassium acetate, and it's the same molarity of potassium hydroxide. The other thing to note here is notice they have different volumes. So these two have the same volume. So same volume, same molarity means same number of moles. So you have the same number of moles of potassium acetate as you do acetic acid. And then half the volume, same molarity, but half the volume would mean half the number of moles of potassium hydroxide that you do potassium acetate and acetic acid. So, just kind of looking at those amounts, all right? And then let's kind of look at each individual solution. So in Beaker 1, yeah, you have KOH, but that doesn't mean you have KOH together. Remember, that's a salt. So when you have a solution of a salt, it's really potassium ions and hydroxide ions. So, most of the time we don't care about potassium ions. So the key thing in here is recognize, hey, I got hydroxide. Hey, potassium hydroxide is a strong base. So if I can figure out the concentration of hydroxide, I can take the negative log of that to get the POH, and then 14 minus will give me the pH. So if they ask me to calculate the pH of Beaker 1, I'm all set. Negative log of hydroxide molarity and then 14 minus. Okay, so that's what's going on in Beaker 1. If they ask me the concentration of potassium, I know it's 0.25. If they ask me the concentration of hydroxide, I know it's 0.25. Why? Because those subscripts are 1 in the compound. And if I want to know how many moles of each one I have, liters times molarity, 0.025 times 0.25 would give me moles of potassium. 0.025 times 0.25 would give me moles of hydroxide in Beaker 1. Okay, let's look at Beaker 2. Beaker 2, another salt, potassium acetate in this case. Okay, so I really don't have this. I have potassium ions floating around, and I got acetate ions floating around. Okay, but notice the subscript for potassium is 1, so the molarity of the compound is the molarity of potassium, and the subscript of acetate in this compound is 1, so the molarity of the compound is the molarity of acetate. Okay, so we have our molarities of our different ions. And what we need to know, especially now that we've been in Unit 5 for a little bit, is acetate is a weak base. So we have a weak base in solution here. So if for some reason they ask me to calculate the pH of the solution in beaker 2, all I'm going to have to do is a weak-base shortcut, KB shortcut. I know the molarity of acetate, so really all I'm going to need to do is know the KB. I got to figure out the KB of acetate, and if I can figure that out, I can solve for X. I got to recognize that X is the hydroxide concentration in this shortcut, so the negative log of that would be the POH, and if I wanted the pH, I'd have to subtract from 14. Okay, so that's what's going on in beaker 2. All right, beaker 3. All right, all I have is acetic acid. It is a weak acid. I need to know that. All right, so what's going on in beaker 3 is really just this. You have this molecule together. It's surrounded by water molecules. It's aqueous, but it hasn't dissociated. And the reason I know it's not really dissociating is because it's a weak acid. It's not a strong acid. So you really don't have H plus and acetate ions. What you have the majority of is just this molecule together. There's a little bit of H plus and there's a little bit of acetate, but not nearly as much as the acetic acid. So what's the majority of what's going on in this beaker? This. And it's a weak acid, so if I was given the Ka of that acid, I could solve for X in the Ka shortcut. I should recognize that X is the H plus concentration, or hydronium, and the negative log of X would be the pH. So if I wanted to calculate the pH in beaker 3, I'd be all set. I'd be all ready to go. Okay? Again, let's go back and look at the question itself. All right, another thing to start thinking about is we're probably going to start mixing things together. Okay? If I mix beaker 2 and beaker 1 together, nothing's really going to happen because potassium's not going to react with potassium, and acetate's not going to react with hydroxide, right? Bases don't react with other bases, right? So mixing beaker 2 with beaker 1 won't do anything, all right? If I mix beaker 1 with beaker 3, all the hydroxide would react with acetic acid, right? Hydroxide reacts with any acid. So mixing beaker 1 and beaker 3, I know a reaction is going to go to completion, and because I already did the math, I have less hydroxide. So after I mix beaker 1 with beaker 3, if that's what happens in the question, I know I'm not going to have any more hydroxide, and I'm going to have half as much of the acetic acid as I started with, right? And I'm going to gain some acetate, right? So another thing to note is if we mix beaker 1 with beaker 3, the resulting solution would be a buffer because you would still have this because you didn't add enough hydroxide to get rid of all of the acetic acid. But as the hydroxide neutralizes and takes the H plus away from this acid, you would get acetate, okay? But another thing to note is you can make a buffer by mixing beaker 2 with beaker 3. Now, if we mix beaker 2 with beaker 3, we would have acetic acid in solution and we would have acetate in solution. We would have the conjugate acid-base pair, and they're weak, and that would be a buffer system. So let's think about it. If we mix beaker 3 and beaker 2 together, we get a buffer. And then if we add beaker 1 to the resulting mixture of beaker 2 and beaker 3, that would be a buffer attack question. So I'm guessing that's what probably is going to happen. We're going to have to know what happens when we mix beaker 3 and beaker 2 together, and then what happens when we take that buffer solution that we made by mixing these two beakers together and we attack it with strong base. All right. But let's just go question by question now. All right, here we go. So question A, determine the pH of beaker 1. Well, we already said how to do that. Negative log of hydroxide, subtract from 14. So let's go ahead and do that. Okay. So negative log of hydroxide gives me the POH, and then subtract from 14 gives me the pH. So 13.398. That makes sense. KOH is a strong base. We have a pretty high concentration, 0.25 molar of it. So it's going to have a pretty high pH. Okay. So let's go to question B. All right, say, hey, they're asking us, let's not get ahead of ourselves. They give us the Ka of acetic acid, and they want to know the hydronium ion concentration in beaker 3. Okay, so not necessarily the pH. So we're still going to use our Ka shortcut, but we're going to stop at X. We're going to solve for X, and that is the hydronium concentration. Okay. Another thing to note, side note, they gave us the Ka for acetic acid. So Kw divided by this gives me the Kb of acetate. Maybe I need it, maybe I don't. But anytime I'm given a Ka, I'm given the Kb of its conjugate base. And its conjugate base, in this case, is acetate. So Kw divided by this gives me that. That's the Kb of acetate. I don't need it for question B, but I might need it later. Okay, so all we need to do is plug that Ka into the shortcut. Our concentration of acetate was 0.25. We're going to solve for X. And we got to remember, whenever we're using this shortcut, X is the hydronium concentration. So we solve for X, and that is the molarity of hydronium. Remember, you wouldn't need units for this answer because molarity concentration has unit, right? So the hydronium concentration would be 0.0021 moles per liter, or capital M. Okay. All right, part C. What's the pH of the solution in beaker 3? Oh, well, all we have to do is take the negative log of our answer from part B. So to answer part C, we just take the negative log of this. So the negative log of that will be our pH, and our pH comes out to be 2.68. And that, again, that should make sense. We recognize acetic acid as a weak acid. So if we have a weak acid in our beaker, our pH should be below 7. Okay, there we go. All right, part D. Calculate the pH in beaker 2. All right, so that understanding that given the Ka of acetic acid, we were given the Kb of acetate. That's great because we need it to answer part D. So part D, we're going to do a Kb shortcut with acetate because we know acetate's a weak base. And so if we do the Kb shortcut and solve for X, X is the hydroxide concentration. We'll take the negative log of that, and that'll give us a POH, but then we'll have to subtract from 14. Okay, so we'll do our Kb shortcut. Remember, we calculated that Kb using our Kw and the Ka given to us. So we get our Kb, we have our concentration of acetate, we solve for X, we recognize that X is the hydroxide concentration, so the negative log of that would give us the POH. So 14 minus the POH will give us the pH, and in this case it comes out to be 9.07. And again, that should make sense. We should have recognized acetate as a base, weak base, but a base nonetheless. And if I have a solution of acetate, which we do in beaker 2, the solution should be basic. So it should have a pH above 7. And it does, 9.07 in this case. Okay. Right. So E, so A, B, C, and D, we're just looking at the individual solutions. And now E, we start to mix. We're mixing beaker 2 and beaker 3. So remember, we already said mixing beaker 2 and mixing beaker 3 is going to make a buffer solution. So if we have to calculate the pH of our buffer solution, which they're asking us in EI, Henderson-Hasselbalch buffer system, we're going to use the Henderson-Hasselbalch equation. All right. Another thing, time saver. Okay. Remember, right at the beginning, we said, hey, equal molarities, equal volumes means equal moles. So we have equal moles of our conjugate acid-base pair in our buffer system. That means pH equals pKa. So all we have to do to answer part EI is take the negative log of this, and that's the answer. Okay? But let's understand it, right? So we're thinking buffer. We made a buffer solution. So we use the Henderson-Hasselbalch equation. That's this equation. It's on our formula sheet. So remember, on our formula sheet, it says A minus over HA. So that would be acetate over acetic acid in this case. But remember, these two numbers, the molarity of this and the molarity of this, would be equal to each other. So the log of 1 is 0, so pH equals pKa. So we already pointed out that we had equal moles. We knew that going in. So EI is just the negative log of the Ka, and that comes out to be around 4.74. So the pH of our resulting buffer solution after mixing beaker 2 and beaker 3, pH is 4.74. Okay? All right. So that was easy. Okay, part F. Now, buffer attack question. So beaker 1, which is our strong base, is poured into the resulting mixture of beaker 2 and 3, which is our buffer solution. So what are we doing? We're taking our buffer solution that we made and we're attacking it with strong base, buffer attack. So we should be thinking BCA chart, okay? But before that, they ask us, write the chemical reaction that takes place. So we're adding hydroxide to a buffer. Hydroxide's a base, So it's going to react with the acid component of our buffer. So let's review. Our buffer system is acetic acid, that's the acid component, and acetate, that's the base component. And we're adding strong base in this attack. So the strong base that I add is going to take out acetic acid and give us acetate. If it had been reversed, if we were adding strong acid, the strong acid would be taking out acetate and producing acetic acid. Okay? So the reaction that's going to be taking place is hydroxide plus acetic acid yields water, right? The H plus and the OH minus form water, and then you're left with acetate. And remember, whenever you do a buffer attack, you're always sacrificing one component, the acid in this case, and you're gaining the other component. Okay? So that's the reaction. Notice we don't need to include potassium, it's just a spectator ion. Okay. All right, pH of the resulting solution. So we're gonna have to do a BCA chart and figure out our new amounts of our buffer components and then plug those new amounts into the Henderson-Hasselbalch equation. So we'll make our BCA chart. Remember, before, change after. Remember, we're plugging in moles here. So how do we get moles? Liters times molarity, right? So if I do liters times molarity, that'll give me moles of acetate. Liters times molarity will give me moles of acetic acid. And then liters times molarity would give me moles of hydroxide that I added. Okay, so we need all of those, all right? So the moles of acetic acid and acetate, remember they were the same, 0.0125 and 0.0125, liters times molarity. Now, remember the change is the amount of hydroxide or H plus. It's whatever you're attacking with. In this case, we're attacking with hydroxide. So it's the amount of hydroxide we added, right? And for every one hydroxide in this scenario, for every one hydroxide I add, I'm going to lose one of these and I'm going to gain one of those. And everything's a 1-to-1 ratio. So the amount of this I lose equals the amount of this I gain. All right. And it's equal to the amount of hydroxide I added. So if we do, this is how much hydroxide I added, 0.00625. So we're going to subtract that from the HA, the acetic acid in this case, and we're going to add it to the acetate, A minus in this case. All right. So we do our math, this minus that, and then this plus that. And so we get after, we have both of these. Okay. Now, let's understand. If we wanted the new molarity of acetic acid, we would have to divide by the new volume. And if we wanted the new molarity of acetate, we'd have to take this and divide by the new volume. But we don't need molarity to just plug into the Henderson-Hasselbalch because that ratio, the molarity ratio would be the same as the mole ratio. So we can just plug in moles into the Henderson-Hasselbalch. But if you wanted the new concentration, the new molarity, you would have to divide by the new volume. So let's understand what the new volume would be. Pretty easy. We took 50 milliliters and added to 50 milliliters, and then we added 25 milliliters. So our new volume would be 125 milliliters. So if we had to, if we needed to know the new molarities after the attacks, we would take our moles we found in our BCA chart and divide by 0.125 liters in this case, because that was our new volume. Okay, so you could do that and then plug in the molarity into the Henderson-Hasselbalch instead of the moles. But remember, it's just a ratio that we need in the Henderson-Hasselbalch, and the mole ratio and the molarity ratio are going to be the same. All right, so remember, this 4.74 was the pKa. So we're saying pH equals pKa plus the log of that ratio. And so when we do it, we get pH equals 5.22. Now understand that this should make sense. We added strong base, so the pH should go up. So like if we did this calculation and the pH had been less than the 4.74, which was the original pH of our buffer system, then we know we did something wrong. The pH should increase when you add strong base. Okay, so our new pH is 5.22. Okay. All right, question 3 in part F is asking, is the resulting solution effective buffer? So they're not asking, was the solution that you made in part E an effective buffer? It's asking, after the attack, is the remaining solution still a buffer? That's what they're asking here. And the answer in this case would be yes, because you still have both of these. If we go back to our BCA chart, we didn't completely lose all of the acetic acid. So since we still have both components of our buffer system, the resulting solution is still a buffer. Okay, so yeah. All right. Now, part 4 here it's asking us to calculate the molarity of the potassium ions when everything's mixed together. So, normally we don't care about potassium, and here's just, we don't really care about the potassium, but now they just want us to know the new molarity. So the important thing to know is that the potassium doesn't react with anything. So all of the potassium that was dissolved originally is still dissolved. And so we just need to figure out how many moles of potassium we have after we combine all three beakers, and then divide it by the new volume, which we already said was 0.125 liters, and that'll give us the molarity potassium. So I guess the harder part is that we have two sources of potassium. We have moles of potassium from this beaker, and we have moles of potassium from this beaker. So we have to figure out how many moles of potassium we had in this beaker, how many moles of potassium we had in this beaker, add the two up, that would be moles after we mix all three of the beakers together, and then just divide by the new volume. Okay. So we had two sources of potassium, so we had to figure out total moles of potassium, and our new volume is 0.125 liters. So beaker 1 had 0.00625 moles of potassium. Beaker 2 had 0.0125 moles of potassium. You add them up, that's our total moles of potassium in the three combined beakers, and then divide it by the new volume, 0.125 liters, and we get the molarity of potassium. And, it's that simple because, again, the potassium is just a spectator. We didn't lose any of it. It's not involved in any of the reactions. The potassium that was dissolved at the beginning is equal to the potassium that was dissolved at the end. So it's just figuring out the total moles, because we had multiple sources of potassium, and then dividing by the new volume in liters. Okay? All right. So that's an example of a 3-beaker question. We're doing another one in class. There's another one on your 5-3 assessment. And don't be surprised when you see a similar question on the test. So when I say 3-beaker question, this is what I'm talking about. And you should lock it in. All right? So that's it. That's the second time I went through that presentation, and I did it for you. I almost thought about not doing it, but I said, you know what? I'm doing it. I'm doing it for you, the viewer. Okay, my fans. All right, so have a great one. All right, hopefully that helps.